important thing I want to add on this lecture, that if you have any kind of secondary school physics level problem, you can send to me this particular email ID that is given here, physicsproposal@gmail.com. I will try my best to revert you back, okay, either by video solution or on the email. Okay, and I want to just make simple point that I want to keep the video as precise as possible without without diluting the ideas. I want to give proper explanation, and that's why I won't repeat many things. I will just state the things, okay? Because in video we have luxury to go back and listen it again. Okay, here I'm directly going to the problem. The problem is like this: that a small block is pulled. Okay, that is a small block. Okay, and in this particular question, the weight W is given. Okay, is pulled with the help of a string. Okay, the string pass over a small pulley like this, and it is pulled with the help of an in this direction. Okay, pulled with the help of inextensible thread passing over pulley, the block slowly ascends on a fixed smooth cylindrical surface. Okay, this is a cylindrical surface. Okay, I'm just seeing the cross section view. The pulley P, that is pulley P, and the center C of the cylindrical surface. Okay, these are on the same vertical line. Okay, means P is just vertical above point C. Determine how the tension, okay, the tension means the force in the thread, normal force, the force exerted by the surface on the block, on the block, okay, will vary, okay, as it slowly ascended, okay, slowly ascended on the smooth fixed cylindrical surface with the help of this thread. Okay, so that is the whole statement. Very good question, beautiful question, I should say. And I will suggest you to give 2 and 3 minutes, okay, and give your best, and then come back to for the solution. Okay, you can pause the video and contemplate for 2-3 minutes. If you want, take one more hint. Okay, here is one hint: the Lami's theorem. There are 3 forces which are balanced. Then the Lami's theorem is because 3 equilibrium, they will form a closed figure that is called triangle. And in triangle, the sides are in ratio of a opposite sign. Sides are in ratio of sines of angle opposite to them. Okay. Now, what I am doing, what I will do here, okay, that is the question given here. Okay, I'll just draw the force diagram. Okay, the force diagram will look like this. Just make a copy over here. Just for the reference here. Okay, here in the middle, I make the force diagram. Okay, the force diagram will go like this. Okay, the force in the contact, force exerted by the things which are in contact, and the force exerted by the objects which are in not contact. Okay, the force exerted by the things which are in not contact are called non-contact forces, and that will be the weight W that is given in the question. And the contact forces, the object which are in contact with, okay, the object is contact with this cylindrical surface, and here it will be normal. Okay, the perpendicular force, no friction because the surface is smooth, and the tension like this. And I have assumed, I have taken some angle like this. This is theta and this is phi. And in this particular diagram, okay, I can see where this is theta and this will be for phi. Okay, you could have taken other angles as well. Okay, it's not a big problem at all. So here I will write, because of under 3 forces, because it is going slowly and slowly, the object is in equilibrium all the time. And in the process, as the object ascends, angle theta and phi will change, and accordingly, the normal and tension may change or may not change. Or if they change, how do they change? Either they increase or decrease. Or, okay, or we cannot determine about it. Okay, so here I'm just draw the force diagram, and this force diagram, and writing the Lami's theorem for it. That is the force divided by sine of angle between the other 2 forces. Okay, that is the Lami's theorem. Proof is given in the next page. Okay, I will just show it. Okay, that nothing more than that that can be derived from the help of the vector equations. The tension, okay, the magnitude of force, and the sine of angle between the other 2 forces. That is a T. Okay, I assume this angle is phi. This angle will be 180 minus phi. Okay, So here that is the first term, and the second term that is the normal and the sign of angle between the other two forces, and that angle will be 180 minus theta. Okay, and the weight, the sign of angle between the other two forces, they are normal and tension. It is sin theta plus phi. Okay, that is we can conclude from the equilibrium equation of a particle under three forces. And okay, one more thing you can also interpret from here. Okay, when the thread of the length decreases, because it will, when it ascend, the length of the thread will decrease. From here you can also interpret the equation. Okay, no problem at all. But there is a simple idea as well. Okay, as we have seen, okay, these are the angles. This is theta, and here this is theta, this is theta, and this is phi, and because of that, that is also phi. Okay, so we can also see a relation here. Okay, in the denominator there are sign of some angles which are matching with the angles of a triangle. Okay, and which triangle we are talking about? The point P, one corner is point P where the pulley is present, one point is the C, the center of the cylindrical surface, and point O where the object is present at a given moment. Okay, in this triangle we can say that there are angle theta, and this is angle phi, and the third angle will be the 180 minus theta minus phi, because the sum of angles of the triangle is 180 degree. So in this triangle we can also write the Lami's theorem, and the Lami's theorem goes by like this: the side L divided by the sine of angle opposite to the side. Okay, that is L by sine phi. And similarly capital L, okay, capital L is the fixed length. Okay, that is the distance between the pulley and the center, that is L. Okay, L over the angle, L over the sine of angle opposite to the side, L, capital L. Okay, this is small L, this capital L. L, capital L over sine of angle opposite to the capital L, that is sine of 180 theta minus phi. And the third side is the radius. Okay, R. So third side of the triangle is R, and it will goes like the side divided by the angle opposite to the this particular side, that is theta, in this particular triangle. So here we have two equations, one from the equilibrium equation, laws of motion equation, and one from the properties of the triangle. And you can see here, okay, you will get an idea about the angles here, theta, phi, 180 minus theta minus phi. You can check the denominator. Okay, they are same actually. So I just simplify one more step. Here I will write, I will simplify it here. Sin 180 minus phi sin phi, and sin 180 minus theta is sin theta, and it will remain same. And here it will remain same, it will remain same, and it will go there sin theta plus phi. So this is our equation 3, and this is equation 4. Okay, when we divide this two equation, you can see the denominator will cancel out. Okay, so dividing these two expression, we will get, you can check it out, the T by L, the tension over the length of the thread. Which length of the thread? Which is present on the left side. Okay, the between the object and the pulley. And the second, T by L over T by N by R, that is the normal over radius. And the third term is weight, which is a constant quantity, and length L, which is also a constant quantity. Okay, we will get this equation. And from here we can see the variation of the tension and the normal. We get, because we know that weight is constant. Okay, so we use this equation to get the tension, and we get the tension from this two equal term as small l divided by capital L into weight. Okay, even if the length is given, we can find the actual value of the tension. Okay, that is also plus point. Another thing, that is a normal. Okay, we can find the normal with in terms of the weight, because it's constant quantity. The normal will be the just rearranging the term, the radius by length of the distance between the pulley and the center of the cylinder, that is R over capital L times the weight. So from these expression we can easily see. Now you can comment on the magnitude of the tension, magnitude of the normal. Can you comment over it? Yes, certainly. That here R is constant and length is constant. It means normal will always remain same. Okay, the magnitude of normal will remain same. If you ask about the normal force, okay, it will change because the direction will be changing, but the magnitude of the normal force will remain constant. And in the terms of the tension, okay, you can also easily see over here, the length is decreasing because the object is ascending. The thread of the length on the left side will decrease. Hence, when the object ascends, we can see the tension will decrease. because L will decrease as the object ascending on the smooth fixed cylindrical surface. So that's a beautiful idea. Yes, there are many ways of doing the thing, but simple, elegant solution. People may find it very difficult to solve it with just simple equation. Okay, from here it is, you can try it. Okay, that's elegancy of the solution. That's why I just took a very simple problem in the equilibrium. And here I'm given the proof of the Lami's theorem. Okay, if there are three vectors, okay, which gives a resultant of 0. Okay, then what is the Lami's theorem? That magnitude of the vectors divided by the sign of angle between the other two vectors is a constant quantity. So I'm taking vector A, vector B, and vector C, whose magnitude are A, B, C respectively, and making a closed figure. It means the resultant is 0, and angle between the vectors are given. Between A and B is gamma, between B and C alpha, and between C and A is beta. So I have redrawn this diagram as co-initial vectors, and here we can see. And how to write the equation? Okay, if we have to find the relation between the magnitude of two vectors, okay, how do we know that, how to proceed further? Okay, we can just take the components of two vectors, magnitude of vectors, perpendicular to the third vector. Like this is the vector A. In the perpendicular direction of the vector A, there will be no component of A. Okay, so we'll get the component of vector B and the component of vector C as balanced. And from here we get the relation like this. I'm getting the component of B perpendicular to the direction of A as B sine gamma. You can check it out, just some trigonometry. And the component of vector C perpendicular to the vector A. Okay, and from here we get this relation. And similarly, okay, that we have to do the same thing. Now we are taking the components of the two vectors perpendicular to the another vector. Here we have taken the components of the two vectors perpendicular to the vector A. Here we are taking the component of the two vectors perpendicular to the vector C. So here there will be no role of the vector C. And we are balancing the component of vector B and vector A in the perpendicular direction of the vector C. So from here, we'll get another relation. It is the second relation. Okay. So here we are getting the relation between the sides and the angles of the triangle. Okay. You can make the third triangle and can also find the third ratio, or you just divide these two equation and can finally find the third ratio. And dividing these two equations, this is the first equation and this is the second equation. If we divide it first, divided by 2, okay, whatever was divided by 2, we will get A by C as sine alpha over sine gamma. Okay. So from here we can conclude from these three equations, that is equation 1, equation 2, and equation 3, that A is proportional to sine alpha, C is proportional to sine gamma, and B is proportional to sine beta. That is the proof of the Lami's theorem. Okay, it is a very useful theorem that magnitude of vector divided by the sign of angle between the two other vectors. Okay, that is a constant quantity. Okay, thanks for watching the video.